65 Celsius. Wheat starch gelatinizes at a lower temperature. So if you want to use some wheat in your mash, you can do without any problem. You can put some wheat in alongside the malted barley and be quite successful at this sort of temperature. But some starches need a higher gelatinization temperature. And 3 starches that I'd like to mention in this context are rice, corn, and sorghum. For each of them, the gelatinization temperature is substantially higher than 65 degrees Celsius. And that is why, if you're using things like rice and corn, you need to have a separate cereal cooker. If you go into a brew house where they're using rice or corn, you'll see a cereal cooker. And basically what happens is the slurry of rice or corn grits will be mixed with water and perhaps a little bit of extra heat-tolerant enzyme and basically boiled to gelatinize the starch. Meanwhile, the malt mash, the regular mash of malt, will be at a lower temperature than needed. It may be at, say, 45 degrees Celsius instead of 65. And that's a good thing too, because that allows any leftover cell wall material to be degraded. The enzymes that break down the cell wall material tend to be a little bit sensitive to heat. And if you want to have them carrying on their job in the brew house, you need to start the mashing at a somewhat lower temperature than 65 degrees Celsius. So here we have this main mash of malt at, say, 45 degrees Celsius, and we have our rice or our corn cooked at around 100 degrees Celsius, and now we mix the two together. And of course the temperature of the main mash now rises until we get to, say, 65 degrees Celsius. And the enzymes from the malt are now going to break down the starch that has been gelatinized from the rice or the corn. And so we have now the production of sugars. The rice and the corn don't provide any enzymes, but they're not going to be used at a level much more than 30%. And the 70% malt contains enough of the starch-degrading enzymes to deal with the starch from the rice or the corn. So if you look at a mash cooker or a mash tun or a mashing in vessel, it basically contains a system, first of all, for mixing the milled grist and the water. They are mixed together intimately as they move into the vessel. If you just put all the solid, all the malt, the milled malt into a vessel and put the water on the top, all you'll get is a mess. So you have to mix these two together quite evenly, and this is done by intimately mixing them as they go into the vessel. You have a chute which allows the grain to come in, the milled grist to come in, as the water flows by and carries it into the vessel. There is a rouser, a stirrer in the vessel to help regulate the temperature, to make sure that the temperature is evenly distributed through the vessel. And any heating is now carried out with coils or with a jacket, a steam jacket. And by putting steam in through that jacket, so you can regulate the temperature, increase the temperature. Some of you may have heard of a term called decoction mashing. Decoction mashing is a very historic way of making worts for lager-style brews. And you have to remember the history if you were to make sense of why you have decoction mashing. In those far-off days, some of the malts were not very good. Some of the barley was not very good. And to produce a malt which would work in the brewery, you had to dry the malt at a very low temperature. Now, they didn't know why that was. They didn't know about enzymes in those days. But they realized that they had to dry the malt at a very low temperature, otherwise it would not behave in the brewery. What we now know is happening is that to preserve the enzymes, the malts had to be very lightly dried. If you heat the malt too strongly in the kilning process, you'll kill off the enzymes. And because there weren't as many enzymes as they needed, so they had to dry it very lightly. Again, they didn't know about the enzymes, but that's what they were doing. What that meant was the malt was of a fairly light colour. Hence, historically, many lagers are very pale. Then they found experientially that they had to mash in at a relatively low temperature. And the reason is that because the malts were poorly modified, they still had a lot of the cell wall materials left behind. And these had to be dealt with in the brew house. Again, they didn't know about the enzymes that were sensitive to heat. They just knew that if they mashed in at a low temperature, so they could successfully deal with this malt. But then they realized they had to get the extract, they had to raise the temperature. But they didn't have thermometers in those days, and they certainly didn't have steam-jacketed vessels where they could control the temperature by introducing more and more steam. But any idiot can see if something's boiling or not, so what they did was take out a proportion of the mash and boil it in a separate vessel to basically raise the temperature. And then they added back that boiled sample to the main mash to raise the temperature. And again, it was all done by rule of thumb and dipping fingers in and experiential and working out how many barrels of this and how many barrels of that. But this was the basis of successively raising the temperature. The low temperature to deal with the residual cell wall material, and then the higher temperature to deal with the starch. And that is the basis, that is the history of decoction mashing. There are still some people who swear by decoction mashing. They do not want to raise the temperature in a single vessel. They insist on this transfer between vessels. But it's a debatable need and not one that I can argue or want to argue here. So after an hour or so of this mashing, now we need to separate the wort, the liquid, from the spent grains. And this is where we invoke Mr. Darcy. Now, I'm not talking Pride and Prejudice. I'm talking Mr. Darcy, who came up with an equation to explain the rate of liquid flow from a solid liquid system. And he has an equation. I'm not sure how keen you are on mathematical equations. It's a fairly simple one, and what it says is that the rate of liquid flow equals the pressure times the area times the permeability divided by the bed depth multiplied by the viscosity. Because pressure and area and permeability are on the numerator, on the top of the line, anything that increases those will increase the rate of wort flow. Because bed depth and viscosity are on the bottom of the equation, on the denominator, it means that anything that increases those will slow down the rate of liquid flow. So let's just take them one at a time. First of them, let's take the surface area. So if you increase the area of your, let's call it a filter, then you are going to get more liquid through. It's obvious. The bigger the filter, the more liquid you're going to get through it. That is why wort separation systems in breweries have got a very large surface area. The pressure. If you increase the pressure, you will force more liquid through. So it makes perfect sense that the pressure is on the numerator there, and anything to increase the pressure will speed up the rate of wort collection. Be careful, though. I'm going to explain in a minute that some of the wort separation vessels have got slotted floors. They've got holes in the floor. And if you're not careful, if you push too much pressure on there, you block those holes. So you can only go so far with pressure. The permeability is very much dependent on the particle sizes. And this is why the husk is important. These nice big husk particles keeping the filter bed nice and open. and they have a major impact on the permeability. So on the denominator we have the bed depth, so the further the liquid's got to go, the more slowly you will collect it, obviously. So that's why wort separation systems have got a very narrow, very small depth. And the viscosity, anything to lower the viscosity is going to improve wort collection rates. Now, it would be an exaggeration, but if you think of the difference between water and honey, then you know the difference between a low viscous liquid and a high viscous liquid. Anything, therefore, that increases the viscosity is therefore going to mean a slower rate of liquid separation. The viscosity is very much dependent on the complex molecules that come out of the malt from the cell walls. I've referred to them as polysaccharides in the past, and these are very viscous molecules. If they're not broken down during malting or in the mash at the lower temperatures, they'll cause a problem. And that is why, again, good homogeneous malting and an efficient breakdown of these cell wall materials is so important so that you don't get a high viscosity. So once again, Darcy's law, the rate of liquid flow equals the pressure times the area times the permeability. Anything increasing those will increase wort separation, divided by the bed depth times the viscosity. Anything that increases those will slow down wort separation. So there are basically two types of wort separation system. The one that's most widely used in the world is called a Lauter-Ton, L-A-U-T-E-R, Lauter-Ton. And this consists of something called a false bottom, which is basically a grid with holes in it. And the mash is floated on that. The first thing you do is put a little bit of water above the plates, and then you float the mash on that bed. There is also some knives, some rakes that can be used to slice through the grain bed. And there is a facility for sparging water onto the grains. So the grains are introduced onto this bed and the wort is allowed to flow from it and then is recycled. Recycled until it runs clear, we call it running bright. And then it will be allowed to run into the boiling stage, into the kettle. So the first runnings will be very strong, full of sugars, very high specific gravity. Then, progressively, we will start to sparge with water, so we can sparge out more sugars. Remembering that this Lauter-Ton is very wide, very large in diameter, and the bed depth is very shallow, very small, in keeping with Darcy's law. And so you're running off this wort which progressively will get weaker and weaker. And there's a cut-off point, at which point you collect all of the extract that you want, and then the remaining extract will be diverted elsewhere, perhaps to drain or maybe collected for further processing. So the Lauter-Ton is a very skilled operation. You are regulating the pressure differential across the bed depth. You are regulating the rate of sparging, and you are periodically cutting through the grain with those knives to facilitate liquid flow. It's a skilled operation. Some brewers prefer to use a mash filter. Mash filters consist of many plates, polypropylene plates, that have diaphragms in there which you can squeeze. These plates have got a very small distance between them, so the bed depth is very small, but there are so many of these large plates, large in surface area, that you have a huge surface area. And what you do is introduce the mash into this mash filter, and you can allow the liquid to start flowing, but then you can squeeze. So you can apply a hydraulic pressure to it to squeeze the plates together. And this, of course, according to Darcy's law, increases the pressure, and so you can squeeze out wort. And then you can add water and squeeze again, so you are sparging and collecting strong worts. Some brewers prefer lauter tuns. Some brewers prefer mash filters. It is your choice, and there are pros and cons for each. Either way, the spent grains will go to cattle food. There are some breweries that are nowhere near cows, and that presents a problem. It actually costs a lot of money to dry the grain, so most brewers are not keen to do that. Spent grains are 80% water, so to dry it is not desirable. There are all sorts of experiments carried out on other things to do with spent grains. Composting, you can make them into bread, you can make them into cookies. My old company, we had an idea of extruding them to make snack foods. So we would take the spent grains, add lots of salt to them, extrude them, and then these nice salty snacks went off to accompany beer. So salty you drank more beer, so you produce more spent grains, and so on. But really, if people have the choice between taking nice, dry wheat or soggy spent grains, they tend to prefer the wheat. The wort is now going to go into the boiling stage, and there are several functions for boiling. The first of these is to inactivate the enzymes. Most of the enzymes will have become inactivated in the mash, towards the end of the mash, and during lautering. Lautering actually being carried out at a slightly higher temperature than mashing, because that helps lower the viscosity and increase the permeability. But any very heat-resistant enzymes will be finally destroyed during boiling. We've already said that volatilization is important. It's a negative when it comes to hop aroma often, but you will drive off at this stage some unwanted volatile materials. You also, of course, in traditional processing, isomerize the hops at this stage. You also sterilize the wort. So this is one of the wonderful reasons why beer is so wholesome and lacks undesirable microorganisms. Is because they have been destroyed by boiling. And let me remind you that those hop isoalpha acids are also antiseptic. Another reason why no pathogenic organisms will grow in beer. Two other things. First of these, of course, when you're boiling, you are concentrating. So you are driving off moisture. In fact, many brewers will regulate the boil on the basis of the rate of this concentration, this evaporation. It may be something like 4 or 5% evaporation per hour, and they'll control the process on the basis of the rate of that evaporation. And so if you want to make a more concentrated wort, here is one way of doing it, bearing in mind that it is an extremely, extremely energy-demanding stage. Another thing that happens during boiling is precipitation. You precipitate proteins and other material, so-called hot break or trub, T-R-U-B, and by removing the solids at this stage, it means that you're removing material which otherwise may precipitate in the finished beer, and of course we don't want that. So in achieving good beer stability, it's important to effect this precipitation at the boiling stage. One of the downsides of boiling, well, there are two downsides. One is you can develop cooked characters, and perhaps you don't want those. If you boil too intensely, you can produce some overly cooked character in the product. And another one is you can get some colour pickup at this stage as well. If you've ever sliced an apple and left it, then the apple turns brown. That's due to the oxidation of molecules called polyphenols. There are polyphenols that originate in malt and hops as well, and they can become oxidized in the brew house and give colour. and it's a particular problem if you have very pale beer. If you have a very dark beer, an Irish stout, then this colour formation in the brew house is not very important. But if you have a very lightly coloured product, then it's something you need to worry about. So brewing kettles these days are designed to get good, vigorous boils. What you want is a vigorous, rolling boil. If you look inside a kettle, and please be very careful, because it's kind of hot, it's boiling. You've got all this circulation of wort taking place, and this is important, first of all, to drive off unwanted aromas, this volatilization, but also this helps drive the particles together and produce the good hot break, which is now nice and easy to settle out. If you just have a simmer, and it's very hot, but just is gently simmering, you do not get either the good particle formation or an efficient volatilization. A few years ago, I was doing a piece of consultancy for a brewing company, and they very proudly asked me what I thought of their beer, and I said, well, to me it smells of halitosis. They weren't desperately pleased with that considered opinion, but I was able to tell them that the simple reason was they were not getting an efficient boil in the kettle, and therefore they were not driving off materials that they should have been driving off, and these materials survived into the beer and led to an unpleasant character. I was happy to say they took my advice, they bought a new brewery, and now they win prizes for their beer. Boiling is very energy demanding. There has been lots of interest in finding ways to save that energy. A liquid will boil when its vapor pressure is in balance with the atmospheric pressure. So one thing you can do is lower the pressure above the boiling wort, and then the liquid will boil at a lower temperature. Alternatively, you can raise the top pressure and it will boil at a higher temperature, but you need less time to do it. These are some of the ways in which people have suggested avoiding excessive heating in boiling. But there's always a risk to flavour. And one thing you've always got to be mindful of, and one thing the self-respecting brewer will always be mindful of, is avoiding changes which are going to change the character of the product. The boiling wort now needs to be clarified. So we've carried out this precipitation. We now need to clarify the product. We need to remove that solid. And there are various ways of doing this. And in part, it depends on how you've introduced the hops. I talked about pellets and extracts. There are still some brewers, however, who insist on using whole hop cones. And if that is the case, you have the whole hop material to remove. And this is done using something called a hop back or hop jack. This operates a bit like a lauterton, so you're filtering the wort through the bed of spent hops. Those people who are using hop pellets or extracts will, chances are, use a whirlpool or a hot wort receiver. And I like to say that the whirlpool was an idea of Albert Einstein. Now, my grandmother, when she was looking after me, she would make tea by putting tea leaves in a mug and pouring in boiling water and stirring it around. These were days before tea bags. And she would stir around the tea, and then when it had mashed or brewed, we used to use those words, then she would add some milk and drink it. Being very careful to leave behind the solid at the end of the drinking experience. Albert Einstein made his tea in exactly the same way as my grandmother. The difference is he was more observant than my grandmother. So when he was stirring his tea leaves, he would peer into the top of the mug and see these tea leaves swirling round and round and round until they gathered in a pile in the bottom of the mug in the center. And I like to say, Einstein said, what a wonderful idea for separating trub from hot wort in a brewery. Chances are he didn't do that, but the good thing is that the Molson Brewing Company read his observation and they were the first people to use a so-called whirlpool. A whirlpool is a vessel in which you fire in the wort from the kettle tangentially, so it swirls round and round. It's jacketed, this vessel is jacketed, and you send the wort in and it swirls round, and as it spins around, so the precipitated protein, hop, residue material settles in a pile in the middle of the bottom, and you can run off the bright wort. And this is used in breweries now all over the world. It's interesting, the length of time that the wort is in the whirlpool has got a significant influence on the flavour of the beer, which we'll address later. Finally, we need to cool the wort. These days, most people will use something called a paraflow heat exchanger or a wort cooler. If you imagine your radiator on your car, it's something similar. You have many plates, very thin metal plates, and on one side is the hot wort flowing on one side, and on the other side of the plate is the cooling medium. If you're going to cool to ale temperatures, chances are it's cold water, but if you're going to cool to lager temperatures, it's probably going to be also a secondary coolant, glycol or ammonia. And so the hot wort is on one side, the cooling medium is on the other, and the heat passes across the plate from the hot wort to the cooling medium. And so out comes the other side, wort at the temperature you need for fermentation. You have to be mindful of the fact that you can get leaks in this, and so you have to make sure there are no leaks, because we don't want glycol or ammonia in our beer. Most self-respecting brewers check for that. If you are cooling against water, of course, the water starts to warm up, and in the interest of conserving energy, you can then use that water and push that into your steam generation system, and you've collected some of the heat that you need to heat up the next batch of water. We will also put in some oxygen or air at this time, because the yeast needs some oxygen to make the membranes that it needs for growth. One other traditional way, less used these days, of cooling wort is a so-called cool ship. A cool ship is a very large tank at the top of a brewery, placed right at the top of a brewery underneath the roof. And the roof had openings in it to allow the evaporating steam to pass through out into the air outside and allow cooling. And this cool ship was on a slight slope, such that as the wort cools, the solids which separate out from it, so-called cold break, we've had hot break in the kettle, now we've got cold break, those solids, which many brewers feel you shouldn't have either in the wort, they would slide down to one end of the tank and allow you to collect cool, clean wort from the rest of the vessel. Problem, of course, is that birds would land on the roof and deposit who knows what into the wort. So it was less than perfect hygiene-wise. That is the brew house, ladies and gentlemen. In the next class, I will look at yeast and how brewers use the yeast in fermentation to produce beer.
This ends Lecture 6. If you borrowed this course from a public library and would like your own copy of the course guide for future reference, call Recorded Books at 1-800-636-3399 and we'll send you a free copy. A shipping charge will apply. Brewmaster's Art, The History and Science of Beer Making, Lecture 7. Fermentation through Packaging.
In the last class, we talked about the hot side of the process, the brew house. Moving now into the fermentation and downstream processing right the way through into the finished package. And the workhorse here in the cold side is brewing yeast, or as it was known as in the Middle Ages, God is good. Of course, they had no idea what yeast was, but they just knew that they could harvest the stuff that came off the top of a fermentation, and they could add it back to the next batch, and that would kickstart the production of the next beer. So God was indeed good. God is good. That was brewing yeast. We now know that brewing yeast is a fungus, a microscopic fungus, Saccharomyces. There are basically two types of brewing strain. There are ale strains and lager strains. The ale strains are known as Saccharomyces cerevisiae, and this is the most diverse type of yeast. And Saccharomyces cerevisiae ale strains were isolated in many parts of the world. Lager yeast was first studied in Germany, in Bavaria. Interestingly enough, it's claimed that it was spirited out of Germany by the Czechs, and this was the yeast that was first used to make the great Pilsner beers in the Czech Republic, or what was then Bohemia, Czechoslovakia. And then the Danes acquired the yeast from the Czechs, and they gave it their own name. They call it Saccharomyces carlsbergensis. And still, in Carlsberg, they will refer to it by that name. Taxonomists keep changing the name, and soon it was that Saccharomyces carlsbergensis became Saccharomyces uvarum. And then, not satisfied with that, it was changed to Saccharomyces cerevisiae lager type. Now it's agreed that what we have is Saccharomyces pastorianus. So the proper name for lager yeast these days is Saccharomyces pastorianus, bottom fermenting yeast. It's an interesting organism in that Saccharomyces pastorianus looks as if it developed by the melding of two strains, Saccharomyces cerevisiae and Saccharomyces bayanus, which is a strain that is used in certain wine production processes. And so these two organisms, eons ago, melded together to form this more complicated organism. So lager yeast is actually more complicated than ale yeast. But there are many, many brewing strains. And some brewers would insist that it makes a formidable difference to the quality of the beer. I would suggest that the blander the beer, or the more gently flavored the beer, the more important the yeast becomes. If you've got a beer that is full of malt character, roast character, hoppy character, then the contribution of the yeast is not always major. It may indeed be minor. Apart from making the alcohol, then you probably won't notice too many flavor nuances. However, if you've got a fairly subtly flavored product, then the contribution of materials produced by the yeast is going to be more significant. A yeast cell is about 10 microns in diameter. That's 10 millionths of a meter in diameter. And around the cell is a cell wall. This wall provides rigidity and strength to the yeast, and it's negatively charged. It's got a negative charge. So if two yeast cells come together, then they repel one another because like charges repel. But if you've got something like calcium there, it can bridge the yeast cells. And therefore the calcium level is very important because it leads to flocculation. Flocculation is where the yeast cells stick together and accumulate and agglomerate, and they either rise to the top of the fermenter, so-called top fermentation, and will be harvested from the top, as was the case in traditional ale production, or when they flocculated, they would sink to the bottom of the fermenter and be collected from the bottom of the fermentation, as in lager production traditionally. These days, those borders, those boundaries are much less, because you have these very, very big vessels, these very, very big fermenters, and the yeast tends to behave similarly in both of them and would sink to the bottom of the fermenter, no matter which type it is. Right inside the cell wall is a membrane. and the membrane regulates what gets into the cell and what leaves the cell. So it's involved in the transportation of sugars into the cell and the shipping of materials, co-products, waste products out of the cell. The membrane needs so-called lipids as well as proteins, and to make those lipids, so-called sterols, then you need a supply of oxygen. That's why you put some oxygen into the wort for those membranes. The cytoplasm is inside the membrane, lots of enzyme action going on in the cytoplasm. And there are one or two other organelles, but the most important one I draw attention to is the nucleus. The nucleus of the yeast cell, like the nucleus of other cells, is the repository of genetic information. This is where you have the chromosomes, the DNA. And Saccharomyces cerevisiae consists of 16 chromosomes. Brewing strains have got several copies of these chromosomes. They're said to be either aneuploid or polyploid. They've got several copies. This means that yeast strains are fairly stable. If they're careless and they lose one copy of a gene, they have another copy, at least one more copy, to fall back on. And that's why yeast strains tend not to change too much with time. They will change, they will evolve, but only slowly. Yeasts reproduce by budding. If you look at a culture of yeast under a microscope, you will see little buds appearing. The mother cell starts to grow a daughter cell, and this daughter cell will grow to the same size as the mother cell and then will separate off. So you now have two yeasts. And so the yeast multiplies in this way. When it hives off from the mother, a scar is left behind, the so-called bud scar. And so by counting the bud scars, you can count how many times a yeast has multiplied. And what you want is young and virile yeast. You don't want senile yeast. So by counting the bud scars, you can see just how old your yeast really is. It used to be the case, and still is in some parts of the world, that you would take the yeast from one fermentation and just pitch it into the next fermentation, and so on ad infinitum. Of course, the yeast is successively getting older and more decrepit. It's probably not a good thing. These days, many brewers will actually repropagate every so often. They may use the same yeast successfully 3, 4, 5, or 6 times, but then they will repitch with new yeast propagated from a fresh starter culture. So many brewers are choosy about what yeast they use. I would like to suggest that brewers, more than the producers of some other types of alcoholic beverage, are rather more demanding about the selection of their yeast strain. And if you want to know what yeast you've got, there are basically 2 ways of doing it. The first is by a so-called phenotypic approach. You can see what sugars the yeast utilizes, what its flocculation characteristics are, what the balance of materials it produces are. All these are characteristic of a given yeast strain. Or, analogously to what we did with barley, we can use forensics. We can analyze the DNA pattern from the yeast, and we can decide which yeast strain we've got. And so if you are sent a yeast strain, you want to be confident you got the right yeast strain, this is how you can do it. Remember that there are some brewers in the world who brew beers for different people. I remember one brewery in the south of England that were making 4 or 5 different major lagers for brewing companies around the world, from America, from Australia, and beyond. And all of those companies whose beers they were brewing insisted that they should be using the right yeast strain, their yeast strain. And so using these phenotypic and genotypic approaches, so they could check that they were using the right yeast. Ale strains can be differentiated from lager strains relatively easily. One way is to grow them at 37 degrees Celsius, that is basically blood temperature. Ale strains will grow at that temperature and lager strains won't. But ale strains will not use a sugar called mellibiose. lager strains will use mellibios. That's because the lager strains, with their more complex makeup, their extra DNA from the Saccharomyces bayanus, they have an enzyme, an extra gene to utilize this mellibios. And so if you have a strain that will grow on mellibios, it's a lager strain. Now, yeast requires various materials on which to grow, and the source of those materials, of course, in a brewery is the wort. The sugars provide the carbon and the energy that the yeast can use to make its cells, remembering that what the yeast is interested in doing is making more yeast. The beer is actually an excretion product. It's one that we're rather interested in. And we have to have this compromise. We have to allow some degree of yeast growth if we want to get the beer we want, but we don't want too much yeast growth, just the right amount. And the yeast grows using the energy and the carbon from the sugars. The nitrogen that the yeast needs to make its own proteins, it will get from the amino acids in the wort, the amino acids that have been produced during malting and mashing. It needs some sulfur, and that also will come from amino acids, but also from things like sulfate. Remember, there's a very high level of sulfate in the water from Burton-on-Trent. The yeast needs a little bit of oxygen to make its membranes, as I've said before. And yeast needs some minerals, and one of the most important minerals is zinc. Of all the materials, all the minerals that are likely to be limiting for the yeast, it would be zinc. Yeast needs zinc because it is part of the enzyme that makes the alcohol. And if you have insufficient zinc, you won't make that enzyme and you won't get efficient yeast growth and fermentation. So many brewers will add a little bit of extra zinc to the fermentation. So let's just reprise the difference between ales and lagers. And we'll address this some more in the next class when we talk about beer styles. Ales are made with top fermenting yeast, which are fermenting at relatively warm temperatures, say 18 to 22 degrees Celsius. And what they're using is a wort that has been made from a well-modified malt, one that's been germinated for a long time and dried at a fairly high temperature. And then finally, we have this dry hopping to get the intense hoppy character. Lagers are made traditionally with bottom fermenting yeast that ferment at lower temperatures, as low as 6 degrees Celsius in some traditional breweries in Germany, and not usually at temperatures much higher than 15 degrees Celsius. And the wort's traditionally from malts that are less well modified and relatively lightly kilned, hence the low colour, and of course with this late hopping, where some of the hops are added late in the kettle boil. These days there's a lot of overlap between those two styles, as we shall see in the next class. But again, one thing that nobody will compromise on is the yeast that they will use. So how do you select the right strain for you? Well, serendipity comes into play. Say you want to make a new beer, you would go to a yeast catalogue. There are a number of wonderful suppliers of yeast across the world, and you would buy some yeast and you'll try them in your wort and see which one you like the best. Another useful approach is theft. We've already heard about some examples of this. I remember a boss of mine walked past an open fermenter once, a square fermenter, and ran his handkerchief across the top of the fermenter and collected some yeast from it and brought it back to Burton-on-Trent and encouraged us to isolate what we could from the handkerchief, and certainly a beer was brewed based on that yeast. You can produce new yeast by mutation, but that's not very easy because they have these multiple copies of the genome. A yeast does have a sex life under the right circumstances, so you can breed new strains that way. But the easier option is genetic modification. As soon as I use those two words, many people fly up in alarm. All I would say is that at this point in time, there are no genetically modified yeasts used in the brewing industry. there are no genetically modified cereals used in the brewing industry either. And the reason is there's great concern in the brewing world about the impact that that's likely to have on consumer perception. Nobody wants to be the first one to put the toe in the water. A number of years ago at the research location where I was the director of research, we did actually develop a genetically modified yeast. And this yeast was used to make a beer in our pilot brewery. We called it Nutfield Light. It was a light beer. And we presented the beer and the yeast to the British government, to all sorts of committees on environmental risk and safety and so on, and it was approved for use. Nobody has ever used it. It's sitting in a refrigerator, and I don't know that anybody will. You see, one of the reasons is that the cost of the raw materials, as I've said before, is relatively low. It really doesn't make sense to run any risks. If anybody could genetically modify bottles, it might be a different story, because they are a substantially larger component of the cost equation. The yeast needs to be alive. It needs to be viable. And we test this viability by staining with methylene blue. If you give a yeast cell methylene blue and it's alive, it will take the colour out of the methylene blue and appear colourless. If it doesn't do it, it's dead, and it's only active yeast that will ferment. There's a second concept that brewers talk about, and that is vitality. Remember that we talk about the pitching of yeast. And when you put yeast into a fermenter, it's pitching. If I was to illustrate the concept of vitality, it would be analogously to this, and I would compare myself with Tim Lincecum. We are both viable, but only one of us is fit for pitching. And so the concept of vitality is one of appropriateness. It's more than being alive, it's also being fit for purpose. Nobody has a good measure for vitality yet of yeast, but it is a concept which is developing in importance. And the other thing you have to do is to pitch exactly the correct amount of yeast. You can measure yeast count using something called a hemocytometer. It's a microscope slide which is divided up into grids, and you can count how many yeast cells in each grid. And therefore you can get a measure for how many yeast cells you have, and so you can pitch in the correct amount of yeast. The rule of thumb is that you pitch in 1 million cells for every milliliter of wort for every degree Plato that you have. So if you have a 10-degree Plato wort, you're pitching in 10 million cells for every milliliter. That's a lot of yeast cells. But it's got to be that amount, the right amount, to get the right fermentation program. We monitor a fermentation by measuring the decrease in the specific gravity. In an earlier class, I talked about specific gravity and extract, and I said sugars will increase the weight per unit volume of the wort. Alcohol, I've already said too, has got a specific gravity less than 1. So when you convert sugars into alcohol, the specific gravity goes down. The other thing that goes down is the pH. The pH of wort is in the mid-5s, around 5.5. It's slightly acid. The pH of beer, most beers, is around 4. So it's quite acid, quite sour, as we shall see in the next class. You also produce alcohol, ethanol, which we're glad about. And you produce more yeast. In fact, during fermentation, you probably produce 3 times more yeast than you put into the fermenter. And this is that compromise, producing not too much yeast, but not too little. And during fermentation, that yeast will also, as well as producing alcohol and carbon dioxide, produce a range of flavoursome substances that we will address in a later class. What about this surplus yeast? Well, for fermentations that don't produce too much alcohol, then you can reuse the yeast. You can put the yeast into a succeeding fermentation, and produce beer with it. God is good, after all. Surplus yeast can go to pig food. Pigs love it, particularly because it's got some alcohol left behind in it. Or if you're British or an Australian or New Zealander, then you delight or may delight in Marmite or Vegemite. This is basically autolyzed yeast, which is made into a black spread that you put onto your toast. And I make no apologies for saying this because this is how Marmite is advertised. You either love it or hate it. And it depends what your mother did to you as a baby. If she put her finger in the jar and stuck it in your mouth, you love it. If she was kinder than that, you hate it. My wife loves it. I don't. A range of flavour compounds then from yeast. We produce higher alcohols, which gives a certain degree of fruity character. Acetaldehyde, which gives a green apple flavour, unless it's converted into alcohol, which is what we want to happen. Esters, which give fruity flavours. Fatty acids, giving anything as diverse as wet dog and goatee. Diacetyl, giving butterscotch, which we don't want. And a range of sulfur substances that we'll address in a later class. So there are many types of fermenters. There are open square fermenters, which are literally just big open vessels, historically made out of slate or copper. These days they may be made out of aluminum, stainless steel. Or so-called cylindroconical vessels, which are tall vessels that can be located outside the building. And these have large cylinders, a large cylindrical body, and then a conical base. And they have got cooling jackets in them. Cooling jackets that will allow the fermentation temperature to be regulated. When the yeast is fermenting, it produces alcohol and carbon dioxide, but also heat. And by putting a cooling jacket around the fermenting wort, so you can regulate the temperature and keep it consistent. If you don't do that and it warms up, that will change the flavour spectrum of the beer that you produce. So you regulate the temperature, and then as the yeast ferments and flocculates, it settles to the bottom of the cone and can be harvested and collected from that cone. And once the yeast has been removed at the end of fermentation, so can the beer be removed from the bottom of the vessel as well. These, like all the other vessels in the brewery, are fastidiously cleaned in between batches. We have a process called in-place cleaning or cleaning in place, CIP, where the vessels are rinsed with water and then rinsed with either sodium hydroxide or acid, and then more water, and then sterilized with a sterilant. And in this way we make sure that hygiene is maintained. I said that yeast during its fermentation will lower the specific gravity and produce alcohol and carbon dioxide. When you've produced all the alcohol you can, and you've removed the sugars and the specific gravity has decreased to its minimal value, that is not the end. Because during fermentation, in all brewery fermentations, you produce a molecule called diacetyl. If you've ever smelt popcorn or butterscotch, you know what I'm talking about. That is what it smells like. And few beers benefit from the aroma of popcorn or butterscotch. But this is a product made in the fermentation, and it leaks into the beer. The good news is that yeast will remove it again, but it takes time. The yeast has got enzymes that will so-called reduce the diacetyl and take it to forms that no longer are flavour active. But you have to wait a while for that to happen. So what you need to measure in a brewery fermentation is the time taken to remove this diacetyl. Once it has been removed successfully, then you can go on to the next stage. Some brewers mature the beer with beechwood chips. Well, one brewer matures the beer with beechwood chips. This is to provide a large surface area on which the yeast and other solids can accumulate, and it helps ensure that you remove the last traces of unpleasant things like diacetyl. Most brewers will chill the beer then to -1 or even -2 degrees Celsius to chill out and precipitate out unwanted material, precipitate out proteins, which otherwise will jeopardize the stability of the beer. This is so-called cold conditioning. And the temperature is very important. It's important to get to as low a temperature as possible without freezing the beer. You don't want to freeze the beer because you've got all this ice to deal with in the brewery. But if you take it to a really low temperature, short of freezing it, you will precipitate out unwanted material. Beer does not freeze at 0 Celsius, 32 Fahrenheit. That's because the alcohol and other dissolved materials lower the freezing point. Finally, we're going to remove those solids. Some brewers will use centrifuges to remove yeast cells. Some brewers will use isinglass finings. The isinglass finings are proteins that come from the swim bladders of certain fish from the South China Seas. I'm not quite sure how this was first discovered, but somebody, somehow, extracted the swim bladder from the fish and dissolved it in acid to produce a solution of collagen, and what that does is stick onto yeast and other solids and makes a settleable material which descends to the bottom of the tank, and in traditional English ale production to the bottom of the barrel, to clarify the product. It's still widely used in some parts of the world, but not very much in the United States. The majority of brewers worldwide will filter beer through kieselguhr, otherwise known as diatomaceous earth. Diatomaceous earth is the skeletal remains of diatoms, organisms that lived many years ago. And these have got all sorts of pores and high surface area associated with them that are very good at trapping particles. One good source of this material is the coastline near Santa Barbara in California, a place called Lompoc. Lots of kieselguhr. And this is used in filters to help clarify the beer, to remove yeast and other particles. Some people prefer to use perlite, which is a volcanic ash. Usually not quite as good as kieselguhr, but nonetheless quite effective in helping separate out insoluble material for those beers that are intended to be bright. Downstream of the filter, there may be some form of stabilization. Some brewers remove excessive protein. They use silicas that are derived from sand. Some people use something called PVPP, which removes polyphenol. Polyphenols and proteins will stick together to form hazes in beer. At the end of most fermentations, there is not as much carbon dioxide as you would like in a bottle or a canned product. Indeed, so much carbon dioxide is lost during fermentation. So to make the highly carbonated products that you want in a bottle or a can, there is a need to inject more carbon dioxide, and this will happen downstream. And finally, we will go into the package. In the United States, the bottles are usually one trip. That means they are non-returnable. They are used once. In Canada, they are returnable. And so the beer goes out in the bottles, is consumed, and then the bottles are returned to the brewery to be cleaned and sterilized and used again. The risk to that is you can scuff the bottles and damage the bottles. As it goes down the line repeatedly, you'll scrape off outer surfacing and you will leave white marks which do not appear particularly attractive. Many people prefer the concept of returnable glass, though, for environmental reasons. Just make sure you don't screw up your chip packet and put it in the bottle, because it's difficult to get out again. So the bottle, having been washed, goes to a filler. These mighty swirling machines which contain the beer in a reservoir and heads